Now unfortunately I wasn't able to find out very much information about my KR-2600 receiver, and the information that I did find mainly came from a German hi-fi magazine. Now I have to admit that I'm a little bit embarrassed to say that my understanding of German isn't particularly good, so I was only really able to pick out a few keywords from the information that was contained in this article. But from this article, and also by reading this operating manual of the receiver's big brother, which is the KR-6400, I did manage to find out some additional specification information. Now, some of this may not be particularly relevant to the receiver that I'm using, because the KR-6400 was the big brother, and you know, was one of the much higher end receivers that they were building at that time. But it does still give us some you know, ideas of what we might expect, because it's a similar vintage, and I would have thought that the performance won't be totally dissimilar, although I can actually see though that there is you know, there is some big differences in things like the output power, in that this unit is a 45 watt output unit, whereas the one that we've got is only 15 watts per channel. But I'm hoping that the information that is contained on this specification will be you know, still be relevant and still be a starting point. So I've correlated all of that information together, and what I've done is I've drawn up basically a little bit of a specification sheet for our KR-2600. So the information that I've got came from a magazine that was published in about 1977. So I'm going to take that as the approximate year that our unit was manufactured. But maybe what we can do is open it up and actually have a look if there's a date code on some of the ICs that are in there. Now the power output is listed as being 15 watts per channel, and that's into an 8 ohm load. So that's something we should be readily able to take a measurement on. Now the output impedance, I don't know what that is, but given that it's a solid state amplifier using transistors and output, it's going to be pretty low, and I'm going to take a guess that that's going to be somewhere around 0.4 of an ohm, but that's something maybe we can measure as well. Now the frequency response is listed as being between 20 kilohertz, between 20 hertz and 30 kilohertz, and it's also listed as having a total harmonic distortion as around 0.8%. Now both the power output, well actually all these factors of power output, frequency response and total harmonic distortion, these parameters really want to be measured together, because how these data sheets should work is that this amplifier will produce a 15 watt output over a frequency range of 20 to 30 kilohertz with a total harmonic distortion of no more than 0.8%. Now the power output and the frequency response are really quite easy to measure. Total harmonic distortion is more difficult. In fact, I don't know of a way of doing it with you know, just conventional test equipment. You do need specialist equipment. I believe that some people who have got what you might call a calibrated eye, they could look at a sine wave on an oscilloscope and maybe hear a tone, and maybe they would be able to spot distortion over I think it's around a figure of around 5%, but certainly which is an order of magnitude bigger, but certainly I wouldn't be able to tell a distortion of 0.85% or see it or hear it. So that's not something we're going to be able to measure very readily with what you may call run-of-the-mill test gear. Damping factor. Now I don't even know what that is. I always say I don't know very much about audio equipment, amplifiers. It's not my background area. So I've got no idea what a damping factor is. Maybe if somebody who's watching this knows what that is, you can tell me. And if you know of a way of easily measuring it, even better still, leave it in your comments. Input sensitivity. Well, I found the input sensitivity and I just saw these letters mm. Now I'm not even sure what mm is, so again, if you know what it is, leave it in your comments. I'm guessing an mm input is probably phono, and I'm just going off that based on that it's got a very low input level, which is 2.5 millivolts. So I'm making a guess that an mm is a gramophone input because of the very low signal input level that you would get from a a cartridge on a gramophone. Should you call it a gramophone or a turntable? I bet there's a difference between the two. I don't know what it is. Now, input sensitivity for the line. Well, I haven't got a figure listed for our particular unit, but the big brother, the 6400, that was listed as having a line input sensitivity as 150 millivolts and a DIN input of 150 millivolts as well. And the unit that we have does actually have a DIN connector, which is what I was using to connect it to the 8-track tape recorder. And I found that it didn't work particularly well when I connected my 8-track to it. So maybe that's something we could do a test on to see whether or not it does actually conform to the standard, or if at least the numbers are in the ballpark. Likewise, we've got input impedances here. So I don't know what any of them are, so there's something that we could probably have a go at measuring as well. Signal to noise ratio, 70 dBs, and that's for the gramophone input, and also we've got a specification for the line input, so maybe that's something we can have a look at as well. Other things, tone control. So the big brother, the KR-2600, if you adjust the tone control for 100 hertz, that gives a plus or minus 10 dB effect, and the same for the treble response. So that's something we can test as well. Okay, now we get on to the AM tuning range, 530 kilohertz to 1700 kilohertz. Yep, we can test that relatively easily. AM sensitivity, FM tuning range, we can have a go at testing them. But one thing that I'm not sure about at the moment is that this particular receiver has a 300 ohm balanced input. Now I'm used to using test equipment that uses unbalanced coaxial type feeders with an impedance of 50 ohms. And so I'm not quite sure how to connect our signal generator to this input. Now, there's lots of ways you can do it using resistive pads, or maybe we can build a 6-to-1 balun. But the question I've got is, even if I build one of these things, I won't actually be able to calibrate it. And if it's uncalibrated, really, is there a lot of point in actually doing these measurements? I think maybe we'll have to have a go, but whether they'll be valid or not, I don't know. So, as you can see, there's lots of things we can measure, and I don't think we're going to get through all of these today. So what I suggest we do is actually we go for the low-hanging fruit and just try to do some of the easier measurements. So with that in mind, let's have a look at what we've set up. So we've got our KR-2600 receiver here, and we've got that connected to a signal generator via the line-in connection. Now I am going to be driving both the left and the right hand channels, so I'm effectively driving these from the same source. Now the signal generator that I've got is got a 50 ohm output impedance, and that's fine. A lot of people talk about impedance matching and things like that. Probably the input impedance of the amplifier is, I'm going to suggest for the line input, it's probably around 10 kilo ohms. I don't know what it is exactly, but it really doesn't matter about these output and input impedances not being matched. Really, the only time you have to worry about this is as the frequency starts to increase. Now, if your cable's length is significant compared to actually the wavelength of the signal, then you can have a problem. But I think the wavelength of this 1 kilo ohm, the wavelength of this 1 kilohertz signal that we're going to be using, it's probably something like 200 kilometers into a typical velocity factor cable. So our short half-meter length cables are insignificant. But a lot of audio people seem to get all very excited about these input and output impedances, and you know, some websites go to great pains to actually say how you should be using matching resistors and terminators and stuff like that. And some of the websites go on great pains to describe that you must do this, whereas other audio websites just seem to negate it altogether. So yeah, you know, do what you want, but it's not going to be a problem. So there's a big mismatching of impedances there, but that really isn't a problem at audio frequencies. And in fact, to actually have a very stiff output source going to a very high input, high impedance input is actually pretty desirable. So we're not going to have any problems with mismatch of impedance there. Now, as well as feeding the line inputs, we're also going to be feeding channel 1 of our oscilloscope. So as we do a frequency sweep, what we want to be very sure of is that the signal generator is producing a completely flat output. It doesn't vary. Now the signal generator I'm using, it's a relatively modern digital signal generator. It's I'm just trying to look at it now. It's a, for those playing at home, it's a Furley Fandar TG1304 programmable function generator. And I say it's modern, it was probably built in the 90s or something like that. It's modern compared with a lot of the equipment I've got. And the output frequency, the output level on this is really very flat. I'm assuming it's got some kind of internal monitoring on it. And basically you program the numbers on the front, and what you program in is what you get out. But not all signal generators are like that. I've got an old Farnell signal generator, which is a conventional analog unit that I use for most of the time because it's convenient, and I know that the output level from that isn't particularly flat. It varies as you increase the frequency up and down a little bit. So what we're doing is we're going to monitor the input to the amplifier. We're going to monitor it with the oscilloscope, and we're just going to make sure that as we do the frequency sweep that the input level doesn't change. Now the outputs of the amplifier, we're going to connect them to some dummy loads, which are effectively just big resistors. Some people make a big fuss about saying you must use low inductance resistors and this, that and the other, but the reality is it doesn't make a huge difference, and especially for the kind of tests that we're doing, you know, we're not working in a lab or anything like that. But the resistors that I'm using are quite large ceramic resistors, which are designed to be low inductance, so we're all good there. Now you might be able to see that I've put a triangle there, and which has got an earth symbol in it, and I'm just drawing your attention there. Maybe something you need to be aware of if you're going to be doing some of your own testing is when we actually connect the ground side of the oscilloscope to the output from our amplifier. Some outputs and amplifiers are effectively floating, and they may not like being grounded. This is probably going to be a problem on more modern amplifiers that have multiple outputs that use what they call a bridge type configuration, where it's possibly not a good idea to ground them out. Sometimes you can get away with it without any problems, but yeah, sometimes it can really ruin your day. Now we've got a left and a right channel here, but the way I've got it connected is we're only going to look at the left side. If we were being really proper, I suppose what we would do is we would look at the left side and the right side both together, and that might be useful to look for any imbalance between the two, but I've only got two oscilloscope inputs, so we're using them to monitor the left side of the speaker output, and the right side, channel 1, is going to be used to measure the input from the signal generator. So hopefully that's explained the test setup. Let's have a look at that now on the bench. Now at the moment we've got the signal generator set up to give a 1 kilohertz sine wave output, and the output is 1.94 volts peak to peak. Now the actual output level really isn't too important as long as it's enough to fully drive the amplifier. The reason that I kind of chose this 1.94 volts peak to peak is because it approximates a nice 4 centimetre display on the oscilloscope. So this is the output from the signal generator, and this is going to the input of the oscilloscope on channel 1, which is the yellow channel. And as I said a moment ago, I basically just set that so that it produces a nice 4 centimetre graticule display on the oscilloscope. The actual size of the waveform, again, it's not important for the input. The reason I've chose that particular input is because I've actually got it set up on the graticule lines. I can see if it changes when we do the frequency sweep. I know that something's wrong. It'll tell me that the output of the signal generator isn't flat. So again, the values that I've chosen are pretty arbitrary. I've just chosen them for the purpose of being able to just make a nice, easily readable display on the oscilloscope. So you can choose what you want as long as that input level will fully drive your amplifier. So as I said, channel 1 goes into the oscilloscope and it's joining the line in input to the amplifier here, which is just feeding into the back of the amplifier, and we're feeding both the left and the right hand channels together. Now we've got the output from the amplifier connected into these dummy load resistors, and I've had the amplifier running now for about 20 minutes, so these are actually just getting a little bit warm. I was noticing when I was doing some reading about how to do some of these tests, it just made a point that a lot of the tests start off with the amplifier having been running for an hour or so to warm everything up, and they're actually getting a little bit warm now. So when you're testing any type of equipment, it's actually always a little bit important to make sure everything is properly warmed up. So we've had the amplifier now running for just about half an hour, and I've actually got it set to be outputting. It's approximately 4 watts, but you can actually see that the actual dummy loads that we're using, the 8 ohm resistors, they are getting a little bit warm. They're up at about, what's that, about 35 degrees now, or maybe a bit higher. 40 degrees. I don't know if it's true, but I was told many years ago when I was doing my kind of electrical apprenticeship, looking at heat sinks and things like that. I remember one of the teachers said that quite a good test was if you put your hand on a heat sink or something, if you can just touch your hand to it and hold it on for a second or two without it being painful, that's about 50 degrees. But if you can pick it up and hold it comfortably, it's under that. So yeah, I'm not saying that's a particularly good test, but it seems to work for me. Maybe I've got good calibrated fingers, and I'd say that, yeah, that feels like, I don't know, about 45 degrees to me. So I can pick it up and hold it, but I wouldn't like to hold it forever. Now I don't know if I'm imagining it, but this channel feels a little bit hotter than the other. That's interesting, that. Am I imagining it? I'm a little bit intrigued. Let's just find out. What I've done is I've got these 2 thermocouple cables, and I've actually just glued them. Well, I've sellotaped them onto the dummy load resistors with capped on high temperature tape, and you can actually see that there is a little bit of a temperature difference between the 2 of them, in that one of them's at 39.7 degrees and the other one is at 43. So if I just have a quick feel. Yeah, I can't tell the difference now. This one maybe just feels slightly hotter. Let's just see which lead is which. So I think the one that feels hotter in my hand is that one. Let's just try unplugging it. Yep, so I was correct. Now, before connecting these dummy loads, I did actually check that they were both 8 ohms, and they are practically perfectly 8 ohms, which is interesting that one of them is getting hotter than the other. So the only reason that that can be is because there must be more voltage across one of the resistors opposed to the other. So this is the right channel, and the right channel is getting hot, and the left channel is the one that's staying a little bit cooler. So let's just at the moment we've got the oscilloscope set to the left channel, and I can just see on my screen there it's doing 5.9, let's call it 5.94 volts RMS. 5.94 volts RMS, and our resistance is 8 ohms. So let's just do V squared over R. .94 squared divided by 8 ohms equals 4.4 watts. 4.4. And let's just swap the test leads over to look at the other channel now. .48 volts. 6.49 volts now. That's flicking between the two. So 6.49 squared divided by 8 equals 5.2 watts. That's quite interesting, that, isn't it? So 0.8 of a watt difference between the left and the right channels. I've just checked the balance control and it is set to the centre. So that is interesting. It makes me think that obviously one of the channels, which is obviously the right one, the right channel, must have slightly higher gain because it's providing more output level than the left channel for the same input. So there's obviously some imbalance there, and that's something that I wouldn't have known about. I mean, it makes me think that if I was listening to a piece of music, that 0.8 of a watt's difference, it could be, you know, perhaps quite important maybe. That's interesting, that. And we didn't know that before we connected some test equipment. Now, just reading from our amplifier specification sheet, it does say that the power output from this is 15 watts per channel into an 8 ohm load. Now we went on to say though that was for a total harmonic distortion of less than 0.8%. Now fortunately at the moment I can't do that at total harmonic distortion level. The only thing that I can really do is increase the output level until I can see clipping of the waveform. So basically that's what we're going to do. We're going to increase it until it clips, and then we're going to back it off a bit, and then we'll take our measurement at that level. Unfortunately, I made a little bit of a boo-boo there. This oscilloscope only has the largest volts per division you can go to with this TDS 2022B is only 5 volts per division. And as I was turning the output up from the amplifier, the trace was actually exceeding what I could display on the screen. And although I could have set the vertical position up so that I could have looked at the top of the sine wave, I looked at the bottom, I really wanted to see the whole thing. So what I've had to do is I've just had to go and plug in a ×10 probe, which no doubt is what I should have been using in the first place. So let's just have another go at that. So let's have another go at turning up that amplifier. So I can see if I can turn it right up, the waveform starts to square off. So that's distorting quite badly. So I'm going to back it back down now. I think that's undistorted, and that's 13.4 volts, and I'm going to turn that back down now. So let's just calculate what that actually is. 13.4 volts squared over 8 ohms. 13.4 squared divided by 8 ohms equals 22.4 watts. 22.4 watts. So basically the output of this amplifier was only rated as being 15 watts per channel, but it could actually beat that by quite a few watts. Now, I suspect what was happening there is that the distortion was probably much higher than I could see, even though I backed it off so that I said we couldn't see distortion on the sine wave anymore. There probably was some distortion there, and if I'd had the correct instrumentation, we probably would have seen the amplifier going into distortion much earlier than the 22 watts there that I've just measured. But I'm gonna give this Kenwood receiver a good pass there. Oh, and I probably should have said, and I'm sorry I didn't say earlier, I was doing that test at 1 kilohertz, which is about the frequency that most people do these power output tests. Of course, if you wanted to do it probably more properly, is you would probably pick multiple frequencies, not just at 1 kilohertz, but do them at 50 hertz, 100 hertz, 10 kilohertz, 25 kilohertz, all the way up to the published frequency response figure for the amplifier. But I'm going to give that a good pass. So let's just write that into our table now as a measured value. So we measured 22.4 watts. 22.4 watts. Champion.